Okay, so I'd of course like to start off by thanking John and Cody for putting together this seminar series. It's been really fun. I'll be talking about this paper that came out in the spring with Irene Valenzuela. So first things first, I want to give you the general goal of this talk so that we have a little roadmap for what we'll be discussing today. So in n=2 compactifications of type IIB string theory, we will first of all verify that the weak gravity conjecture is saturated by the BPS D3 brane states that also satisfy the Swampland Distance Conjecture. In doing so, we'll demonstrate that in the asymptotic regimes of moduli space, the black hole extremality bound is equal to a particular force cancellation condition. And finally, we'll use the tools that we've built up to calculate a lower bound on the exponential rate at which these BPS states become massless at infinite distance, which is crucial in the formulation of the Swampland Distance Conjecture. So I think every person that gives a talk on the swampland has to give their own personal depiction of the swampland. Here's mine. So if you take string theory to be our theory of quantum gravity at high energies, then if you take solutions of that theory and run them down in energy, you end up with a set of effective theories that we call the landscape. But at low energies, in addition to that set of effective theories, you may have other effective theories that are seemingly consistent in that they're anomaly-free, but nonetheless, these theories cannot be UV completed into a theory of quantum gravity. And those are the effective theories that we call the swampland. And the swampland program is the task of delineating the boundary between the landscape and the swampland. But to my mind, there's actually two different faces of the swampland program. The first is, I think, what we usually think about in the context of the Swampland program, which has to do with phenomenology. So this answers the question of what physical constraints are there on low energy effective theories that arise from the requirement of a UV completion to quantum gravity. But I think that there's another face of this program that we talk about a little less, which has to do with probing quantum gravity at all energy scales. So asking the question, what structures arise from solutions in string theory, what features, what patterns should we look for? And in this talk, we'll touch on both of these phases. So I'll be particularly focused on two specific constraints from the Swampland program. So let me explain what those are. The first is the weak gravity conjecture. And this statement says, consider a gravitational theory that contains a U1 gauge field. Then this statement says that in order to be a consistent theory of quantum gravity, your theory should include a particle with charge to mass ratio larger than or equal to the charge to mass ratio of extremal black hole solutions of that theory. And I want to stress that oftentimes on the right-hand side here, we just put an order 1 number, but really this is some factor that's specified for you and in principle calculable in the effective theory that you're working in. It's really the extremality bound of black hole solutions. With multiple U1 gauge fields, this statement generalizes quite simply. It now says that the convex hull of the charge to mass ratios of the states in your theory should contain the so-called black hole region. So what do I mean by this? Let's, for example, say that we have an effective theory with 2 U1 gauge fields. And here I'll plot the charge to mass ratio of states under the first gauge field and the charge to mass ratio of states under the second gauge field. And the black holes in this theory live in some region in this space called the black hole region, with the extremal black holes living on the boundary of this region. So all the black holes in the theory will live inside here. Note that this doesn't have to be a unit ball. Oftentimes when we talk about the weak gravity conjecture, we talk about a unit ball, but the shape of this thing will depend on the specific theory that you're working in, and even on the specific direction in charge space that you're looking at. So this is the black hole region, and now if we plot the charge to mass ratios of the states in our theory, then this weak gravity conjecture says that the convex hull of the charge to mass ratios of these states better contain this black hole region. And I'll point out that there's been a colossal amount of work done on the weak gravity conjecture since it was first proposed in 2006. The other conjecture that I'll spend a lot of time talking about is the Swampland Distance Conjecture. So this statement says, now consider a gravitational theory with a moduli space. So now we have some massless scalar fields in our theory. Then, as you traverse an infinite geodesic distance, which I'll call delta phi in the moduli space, then this statement says that there should exist a tower of states with characteristic mass m that goes like some m naught times e to the minus lambda delta phi. So the mass decreases exponentially in the geodesic field distance. This character lambda will be a main character for our talk, so I'll introduce it and give it a name. I'll call it the mass decay rate throughout. And delta phi, I told you, was the geodesic field distance, but it's important to note that it's with respect to a canonically normalized modulus. So that's what I mean. Again, there's been a huge amount of work on the Swampland Distance Conjecture and checking and applying it, but our role in this story will be to check and precisely relate these two conjectures in the context of Calabi-Yau compactifications of Type IIB string theory. But before I go on to talking about checking these conjectures, I want to spend one more slide talking about the physics of the black hole extremality bound. So consider a Reisner-Nordstrom black hole with charge q and mass m. We know that when the charge of this black hole is large enough such that the two horizons of the black hole coincide, this black hole is called extremal. Any larger charge you put on the black hole would result in a naked singularity. And in fact, the process of dumping charge onto that black hole is dynamically forbidden. Now, the extremality bound for such a Reisner-Nordstrom black hole in 4 dimensions in a certain set of units is just 1. So what this tells you is that any black hole in this theory must have charge to mass ratio less than or equal to 1. But, and this is one of the main points of my talk, is that if your theory now includes massless scalars, then this extremality bound changes. So as one example of this, if your theory includes a gauge kinetic term, f mu nu, that couples to some massless scalar field phi with some dilatonic coupling alpha, then the extremality bound now changes from 1 to 1 plus 1/2 alpha squared, where this alpha, again, is the dilatonic coupling that appears in the gauge kinetic function. So in order to check the weak gravity conjecture, we really need 2 things. First of all, we need the charge to mass ratios of the states in our theory. And second of all, as I hope I've stressed enough by this point, we need to know the black hole extremality bounds in our theory. Only once you have these 2 pieces of data can you compare them and really test the conjecture. So that's exactly what we'll do now. We'll obtain these pieces of data in the effective theories that arise from compactifying Type IIB string theory on Calabi-Yau threefolds. So what effective theories are we even talking about? Let me write down the Lagrangian for you. So consider compactifying Type IIB string theory on a Calabi-Yau threefold with H21 complex structure moduli and H11 scalar moduli. But I'll point out that for our purposes, we'll be able to ignore the scalar moduli and talk just about the effective theory for the complex structure side. This effective theory includes H21 complex scalar fields and also H21 plus 1 U1 gauge fields. And the effective action for this sector looks like this. It has a gravitational piece, it has a kinetic term for the complex scalar fields, and it has a kinetic term for the H21 plus 1 U1 gauge fields. And these matrix prefactors, Kij and Nij, or the metric on moduli space and the gauge kinetic matrix, are specified functions. I'm not writing them down for you, but they're completely specified in terms of a prepotential f and also in terms of the complex structure moduli Ti. Now, in addition to the complex scalar fields and the U1 gauge fields, this theory also contains states that carry electric and magnetic charge under the U1 gauge fields. Among these states, the BPS states are D3 branes wrapped on special Lagrangian 3 cycles. And in this paper by Grimm, Palti, and Valenzuela from 2018, they showed that a specific tower of these D3 branes satisfies, in fact, the Swampland Distance Conjecture. Now, these D3 branes, being BPS, have mass equal to the central charge of the state. So the central charge here is Z, and I'll write down an explicit formula for this in a moment, but for now, let's just note that the central charge is a function of a vector of quantized charges, the prepotential F, and the complex structure moduli Ti. They also have charge given by the inner product of the quantized charge vector with itself using the gauge kinetic function in taking that inner product. And furthermore, in n equals to 2 theories, like the one we're working in, you can show that this charge squared can be written as the central charge squared plus the covariant derivative of the central charge squared. Notice that this formula I've just written down is a no force condition. So as we would expect, these BPS states have vanishing self-force. We can see this because on the left-hand side, we have the charge of these states under the U1 gauge fields. And on the right-hand side, we have the gravitational charge, the mass, and we have the charge of these states under the massless scalar fields. So this equation is telling you that these states have vanishing self-force. But we'll also show that in the asymptotic limits of moduli space, these states also saturate the extremality bound in terms of the extremal black holes that I was talking about before. Now, so we have the charges, we have the masses of these states. Obviously, we're going to want to compute the charge to mass ratios. But before we do that, I want to make one more important point, which is that not all charges in the quantized charge lattice can support BPS states. In fact, in order for a black hole in an n equals to 2 theory to be BPS, it has to satisfy this equation that says that the derivative of the central charge evaluated on the horizon of the black hole is 0. This is what's known as the attractor mechanism. It says that no matter what values of the scalar fields you pick at spatial infinity, the scalar fields will always flow to fixed points on the horizon of the black hole. And this attractor flow imposes some restrictions on which charges can support BPS states, independent of the moduli. So these restrictions come generically in this form. So some function, usually a polynomial of the charges, has to satisfy an inequality where this function is calculable in whatever effective theory you're working in. Great. So now we know the charges, we know the masses, and we also know in principle how to calculate which portions of the charge lattice can support BPS states. So we're finally ready to analyze the charge to mass ratios. So I'll start by telling you this fun fact. The fun fact is that because the charge and the mass are given by a single complex central charge Z, the charge to mass ratios of these states form a degenerate ellipsoid in charge to mass space, where this ellipsoid has precisely 2 non-degenerate directions. So let's see how this fun fact follows from a trivial fact. The trivial fact is that the mass of these states is equal to the central charge because they're BPS. And now let's plug in the explicit form of the central charge, which is e to the k over 2, where k is the Kähler potential here, times the quantized charge vector q, times this matrix eta, which is just the matrix 0, -1, 1, 0, times the period vector pi, which is a vector containing the complex structure moduli and also the derivatives of the prepotential. So we'll plug in that form of the central charge, and we'll also write this equation in terms of the so-called charge to mass vector z, which is just the norm of the charge divided by the mass pointing in the direction of the charge. So we plug these things in, and we obtain an equation of the form z transpose a z equals 1, where this matrix A is given explicitly in terms of this matrix eta and in terms of the period vector pi, as well as this matrix G, which can be thought of as the square root of the gauge kinetic matrix. Now, this equation is the equation of an ellipsoid, where the principal radii of this ellipsoid are given by the eigenvalues of this matrix A. But this matrix A has a really cool form. It's essentially the real part of a period vector, a complex vector outer product with itself. And so we know that A has exactly 2 non-zero eigenvalues. Which then tells for us this fact that I stated in the beginning of the slide, that the charge to mass ratios of BPS states form a degenerate ellipsoid with 2 non-degenerate directions, where these 2 non-degenerate directions are given by the 2 non-zero eigenvalues of A. Now let's see how this works in an explicit example. Let me also reactivate the sensor lights. It's annoying me. Let's compactify type IIB string theory on a Calabi-Yau threefold with a single complex structure modulus. So this is the form of the prepotential that I'll take. And in taking this prepotential that has this nice monomial form, I'm really thinking of this prepotential as the infinite distance limit of a whole slew of Calabi-Yau threefolds. And the effective theory that arises from compactifying type IIB string theory on Calabi-Yau with this prepotential has one complex structure modulus and two gauge fields. And furthermore, by using the attractor mechanism, we can show that all charges of the form Q0, Q1, 0, 0 can in principle support BPS states, where Q0 and Q1 are the charges of the state under the electric fields, and 0, the last two entries of this vector, are the charges of the state under the dual gauge fields. And we can go ahead and calculate the charge to mass ratio of the BPS states in this theory, and this is what we find. Again, Q0 and Q1 are the electric charges of this state, and theta and T are the real and imaginary part of the complex structure modulus T. And we can plot these charge to mass vectors. That's what I've plotted here in black dots. So I'm plotting the Z vector that I introduced on the previous slide in charge to mass vector space. And the first thing I want you to notice is that these black dots lie as promised on an ellipse. Let's note that this ellipse is not the unit ball. In fact, we can go ahead and calculate the matrix A that I showed you before, and we find that it's a diagonal matrix with diagonal entries 1/4 and 3/4. And from these diagonal entries, we can just read off the principal radii of this ellipse by inverting the eigenvalues and taking the square root. And we find that this ellipse has principal radii 2 and 2 over the square root of 3, which is really lucky because 2 over the square root of 3 is my favorite number. Now, I told you that having the charge to mass ratios of the states you're interested in is only one piece of checking the weak gravity conjecture. We also need to know the black hole extremality bounds. To do this, we'll first calculate the gauge kinetic matrix, then we'll canonically normalize the modulus. And when we do that, we find that the gauge kinetic matrix has this nice form where it's diagonal with diagonal entries given in terms of exponentials of the canonically normalized modulus T. With these dilatonic couplings, square root of 6 and square root of 2 over 3. And this is awesome because this nice form means that we can use this formula for the extremality bound that I introduced in the beginning of the talk, where the extremality bound for black holes in the presence of these dilatonic couplings to scalar fields is the square root of 1 plus 1/2 alpha squared. And now we can just plug in the values of the dilatonic coupling, so root 6 and root 2 over 3 respectively, and we find that the charge to mass ratio of an extremal black hole charged only under the first gauge field turns out to be 2, and the charge to mass ratio of an extremal black hole charged only under the second gauge field turns out to be, my favorite number, 2 over the square root of 3. So obviously the point is that these numbers are precisely the ones that you saw on the previous slide. And so we find that these states precisely saturate the weak gravity bound. Now, I have a cool example of how this works in a compactification with 2 moduli, but for lack of time, I won't show it to you, but feel free to ask about it. But I'll just mention that in higher dimensional moduli spaces, we see the appearance of degenerate directions from the degenerate ellipsoid that I told you about. We also find that the attractor mechanism non-trivially forbids some charges, so it forbids some portion of the charge lattice. But in any case, what we always find is that in the infinite distance limit, the extremality bound coincides with the BPS bound. Now, I showed you one example, but the real meat of our work was to provide a general formula for these charge to mass ratios in the infinite distance limit of any Calabi-Yau compactification you want to do. And I should say that if you hand me a prepotential, it's quite straightforward to repeat the previous calculation and figure out the charge to mass ratios. But the point is that calculating that prepotential F in general is hard. And so it would be kind of a bummer if we had to rederive it every single time we wanted to do this calculation. But luckily, we can use the machinery of mixed Hodge structures in order to compute the leading behavior of the prepotential near singularities in the moduli space. So this is machinery that was developed by these mathematicians in the first line and applied to Calabi-Yau compactifications by the authors in in the second and third lines. And I'll just give you my little take on what it does for us in this context. Mixed Hodge structures gives you a way to replace your favorite Calabi-Yau. Seen here is the quintic rendered by my colleague Jeff Fertan, and replace that Calabi-Yau with a set of integers, L and D, that characterize the singular limit of the Calabi-Yau's moduli space. And unfortunately, I don't have time to tell you how to compute those integers explicitly, but I want to do a little plug right now because I think we explained really nicely in our paper how to practically compute these integers for in general. And I think it's actually pretty fun and not that hard to do this. And I think it could be really useful for anyone who's interested in studying the physics near the asymptotic limits in moduli space. So that's my little advertisement. Now, I'm not telling you how to compute these integers, but once you have them, we were able to get a general expression for the charge to mass ratios of the BPS states, which has this familiar form. So it's 1 plus something, where now this something depends completely on the integers that characterize the singular limits of the Calabi-Yau moduli space. And this formula is valid up to order, depending on the hierarchies in the moduli near that infinite distance limit. And so this is one of our main results. The other thing we found, though, is that in any general infinite distance limit, indeed, the extremality bound coincides with the BPS bound. Great, so now let's switch gears a little bit and talk about the Swampland Distance Conjecture. So you'll remember our main character, lambda, which was the mass decay rate of the tower that becomes light near infinite distance. Precisely, I'll define it as the derivative of the mass of a given state divided by the mass projected along a geodesic trajectory. And in the formulation of the Swampland Distance Conjecture, this is just some order 1 number, unspecified, but I'd like to convince you that it has something to do with extremal black holes. So for a single modulus, this is really easy to see, because since the extremality bound is equal to the extremality bound is equal to the BPS bound, we can plug in expressions for the charge to mass ratio of BPS states and the charge to mass ratio of extremal black holes. And we find this simple relationship between the derivative of the mass divided by the mass and the extremality bound of black holes. And so we find that the mass decay rate lambda is equal to 1/2 times this dilatonic coupling that's specified for us, the extremality bound. And this was already pointed out in this paper from 2018. But the point is that in higher dimensional moduli spaces, it's not so simple to do this identification because path independence issues make this a little murky. But nonetheless, we can find a lower bound on the decay rate that applies to some states in the theory. And I want to make it clear that this is a lower bound that does not apply to every single state in the theory. In fact, we have counterexamples of states which disobey this lower bound, but what I'm guaranteeing is that in any infinite distance limit, there will be some states that satisfy this lower bound. And again, this formula is completely specified in terms of that integer data given to us by mixed Hodge structures that characterize the singular limits of moduli space. And furthermore, this bound is once again related to the extremality bound of a particular set of black holes associated to the fastest growing modulus in the infinite distance limit. Now, this, I would say, is our main result, but we can use this bound to provide a weaker but more general bound for any Calabi-Yau compactification by plugging in some limiting numbers, which in this case are L1 equals 2 and D1 equals 3 for a Calabi-Yau threefold. And when we plug these in, we find that the overall lower bound is 1 over the square root of 6. And I'll point out that this numerical factor for the lower bound on the mass decay rate was also predicted by this paper, but from a totally different motivation. Okay, so I think we all know that it's sort of tantalizing that the weak gravity conjecture and the Swampland Distance Conjecture both predict light states in the asymptotic regimes of moduli space. And you might be tempted to say that they're just two sides of the same coin. And in this case, what we've shown is that the states that satisfy the Swampland Distance Conjecture precisely saturate the weak gravity conjecture. And I think this fact ties up some loose ends, because both of these conjectures have ambiguities, right? On the one hand, the weak gravity conjecture doesn't tell you which states should satisfy the conjecture. It could be a particle that satisfies the bound, it could be a tower, it could be a sublattice, who knows? On the other hand, the Swampland Distance Conjecture tells you it should be a tower that satisfies the statement, but leaves this order 1 factor unspecified. But I think in this context that there appears to be a single unambiguous statement, which is that in any infinite field distance limit that has a vanishing gauge coupling, there exists an infinite tower of charged states that satisfies the weak gravity bound, which coincides with the BPS bound, and furthermore, that the gauge coupling decreases exponentially in terms of the geodesic field distance, which ties up both the ambiguities on each side. So to summarize, what have we done? We computed the charge to mass ratios of BPS states in these compactifications. We verified that these states saturate the weak gravity bound. We gave general expressions for the charge to mass ratios of these states using infinite distance data using mixed Hodge structures. And finally, we found a general lower bound on the Swampland Distance Conjecture mass decay rate in terms of those black hole extremality bounds. Thanks.
All right, thanks very much, Naomi, for the really nice talk. While we're waiting to see if there are any other questions, let me ask one. Have you thought at all about how moving away from the infinite distance limit will change your bound on lambda?
Yeah, I'm not sure. So the bound on lambda in terms of extremal black holes all has to do with the coincidence of the extremality bound and the BPS bound. So as long as those things still coincide, which it's not clear that they do, but if they do, we'll still be able to give a lower bound on lambda in terms of the extremal black holes.
Okay, very nice. Thanks. And it looks like Ben has a question.
Yes. So you wrote down some condition for to have an attractor solution.
Mm-hmm.
That would be a condition to have a BPS black hole, right? I think
Yes.
That's not a required condition to have a BPS state.
Right. So I think what we were assuming is that if you can build a BPS black hole, that you should also be able to have a BPS state with that charge.
Okay, so you're treating that as a sufficient but not a necessary condition.
Exactly.
Okay, thanks.
Miriam has a comment.
Yes, I have a comment and a question actually. Explicit relationship between the mass and the charge of BPS full set of black holes in n = 4 and n = 8 4-dimensional supergravities has been explicitly derived, also as function of all the moduli and all that. So there you're dealing with lattice vectors of quantized 28 electric and 28 magnetic charges, and you can analyze those relationships in full explicit generalities.
Mm-hmm.
So that's the work with Zeitlin at the end of 95. I should also mention that my suspicion is the example with 2 electric U1 charges that you discuss is a special case of that type. It's pairwise equal for charge, but those are just comments. Well, another question, the question that I do have in connection with that is, of course, in 4 dimensions, we are dealing also with magnetic charges. Mm-hmm. And in this supergravity theories, one can, especially in n = 4 and 8, you can write explicitly the whole set of dionic solutions with the whole explicit mass. So did you think about possible ideas to generalize that to magnetic aspects of the solutions, which of course, in the language of, quantized things are non-perturbative?
Yeah. Thanks for asking that. We totally did think about the dionic charges, and they're actually really interesting because unlike for the case of the electrically charged states, for the dionic case, so let me say, for the electrically charged black holes, the attractor mechanism actually gives you an attractor flow that pushes the moduli to infinite distance on the horizon of the black hole. Whereas for the dionic black holes, there's a non-trivial attractor point at some finite distance in moduli space. And what that ends up telling us in the context of this story with the Swampland Distance Conjecture is that for those dionic states, there's actually no bound, no lower bound on the mass decay rate of the states, precisely because they have this finite distance attractor point.
Right, it's as duality basically at play, at work, you know. For electric one, you go to the, well,
Exactly.
anyway, but okay, thank you.
Thank you.
All right, I think we have time for one more question from Tom.
Thanks. So I was kind of confused about something, Naomi, that you said. I thought you were saying that in this model that you study that there are BPS states for all electric charges. And I think when you're looking at a compactification on a Calabi-Yau threefold to 4 dimensions, there should exist electrically charged BPS states only within the Mori cone and the negative of the Mori cone in the of the Calabi-Yau geometry. So as Miriam was saying, I think in n equals 4 and n equals 8, you can expect to have more BPS states. But in n equals 2, they in general won't fill the entire charge lattice.
Totally. Yeah, that's exactly right. And that's the point I was trying to get across with the discussion of the attractor mechanism. So it is sort of a special case for that one modulus example that I described, that all the electric states can in principle support BPS black holes. But of course, so yeah, it's kind of interesting that in that case, the attractor mechanism seems to allow any choice of charges. But once you start going to higher dimensional moduli spaces, like you said, there's a Mori cone within which you can allow BPS states, which is specified by the attractor flow equations. And in basically all other cases besides the special example that I showed you, there will be some portions of the charge lattice that are cut out by these restrictions. Does that answer your question?
Well, wait, so you were looking at an n equals, an example with two, two U1s, right? So even there, I would expect that the Mori cone isn't going to cover the entire charge lattice.
So it doesn't for dionic states. For if you start including magnetic charges, then there's some non-trivial restrictions on the charges. But for pure electric states, the attractor mechanism doesn't forbid any portion of the charge lattice.
Well, okay. Another comment though is that the Mori cone, which says where BPS states can live, will not in general be the same as the region where BPS black holes live. If you're looking at an asymptotic limit, those things will agree. Mm-hmm. And I guess in this, I think in for the purposes of your talk, you're looking at asymptotic limits, but at a more generic point in moduli space, only a subset of the Mori cone will actually have BPS states that satisfy the attractor equations.
Right. Yeah. In all of this, I'm thinking of the asymptotic limit where, if you like, the Mori cone and the BPS cone align.
Okay, yeah, thanks.
Okay, great. Thanks very much, Naomi.